We're partnered with NASA and part of the heliophysics education activation team. So this group called NASA HEAT, and my collaborators are listed here on this first slide, and as you see, several of them are citizen scientists. They're amateur radio astronomers, and they're part of our project, helping out. And ultimately, you know, our goal is to increase knowledge, awareness of science using radio astronomy as the vehicle, essentially. And so tonight, again, I'm happy to talk to you, and I don't know how many of you are familiar with radio astronomy, so I'm going to give a very brief, introduction, and then talk about Radio JOVE and what we're calling Radio JOVE 2.0. Now, we just made a switch from single frequency to multi-frequency instrument, and I'll talk a little bit about the citizen science that we do at Radio JOVE. I'm totally informal about all this, and I'm perfectly happy if anyone has a question. If you want to raise your hand on Zoom, or if you're there in the room and you want to just talk, then just please ask a question if you'd like to, or we can wait till the end. Either way. I think I have 20 slides. I hope that's not too many. So I'm going to try to keep this to 40 or 45 minutes if I can. So of course, why do we do radio astronomy? Why do we do astronomy in general? Of course, we're interested in learning about the universe, and of course, radio astronomy is just a different way of doing that. And one of the slides I like to show, or the pictures I like to show here, is the optical view of the M81 galaxy group here on the left, and then the 21 centimeter hydrogen, atomic hydrogen map, radio distribution map on the right-hand side. And you see the things look totally different. You would not, maybe in the optical, you would not make the association that these galaxies are interacting with one another, but in the radio, there's no doubt that the hydrogen lines are showing up, and you're seeing the gravitational interaction between these galaxies. So, with any other wavelength, you're going to get a different view of the universe, and so too with all the radio bands that we use. And on the very right-hand side, you see some of the major discoveries in radio astronomy. So cosmic microwave background, of course, was a big one, and the mapping of the Milky Way galaxy and the detection of radio galaxies. Of course, the first detection of a neutron star as a pulsar was done with radio. You can discover exoplanets and see gravitational lensing of galaxies in radio. And of course, the most recent major accomplishment in radio astronomy is these fantastic images of the supermassive black holes. I forget the first one. Was it the M81 or no, M87? I'm sorry, M87 galaxy. And then of course this one, they finally released just recently, the supermassive black hole at the center of the Milky Way. So it's incredible. The technology, as you know, in all aspects of science, has over the last 20-25 years is made incredible leaps and bounds, and no different in radio astronomy. So the technology integrating different telescopes has really made significant advancements in big arrays now. The resolution in at low frequency, long wavelength radio astronomy is really opened up basically a new window into astronomy. So we're using low frequency. This is the HF radio band, so somewhat in the 15 to 30 megahertz range. And has anybody ever heard what the sun sounds like? Here is a snapshot view. These two images show you a spectroscopic view of a recent solar event. Oh, sorry, that's not too recent. That's May of last year. I apologize. In between 15 and 30 megahertz. And then on the right-hand side is a single frequency observation of the same event at 20 megahertz. And here's what a little snippet of the sound, converting the 20 megahertz data into audio. Here's what it sounds like. Well, that's not that impressive. I apologize for that. It's not coming across very strong, even out of my speaker. So let me try another one here and see if this one works. This is another single frequency type 3 solar burst. Let's see if we get this one. Interesting. I'm not sure why I'm not getting a good sound profile there, but you heard the white noise increase when the sun blasts a solar burst, and then an associated radio wave coming from the plasma, the electrons, the plasma in the magnetic fields from the plasma that's kind of blasted off the sun. So like like any astronomy, essentially we're doing remote sensing. So we can record these sounds, record the data, work backwards and try to understand why we're getting these radio waves generated in the first place. And understand the mechanism, understand the environment, the plasma, the magnetic fields, about why these things are happening. So let's try one more here, and this is Jupiter. So we use our radio telescopes to monitor Jupiter, and so here's one type of Jovian radio burst. Let's see if this one comes through.
Following is Jovian S-burst activity.
So the pops that you're hearing there, and you can sort of see the spiky nature at a single frequency on the graph here. So this is an intensity versus time plot. You can determine identify that those signals are actually coming from Jupiter. And I won't go into a whole lot of detail here, but essentially it has to do with an electrical connection between Jupiter and the moon Io. So as you know, Io is volcanic, and so there's a giant torus of plasma at the location of Io's orbit. So the magnetic field lines that run through that plasma then allow some of those electrons will connect back to the planet, and you get a source of plasma there. And so these emissions, similar to auroral emissions on Earth and the auroral emissions at Jupiter and the other magnetic planets, you get auroral type radio emission coming from Io plasma torus as a source. So if you have advanced equipment, you can actually record the sounds or the signals at high speed and play them back slowed down. So here's what they sound like. So some of you may be familiar if you're ham radio or work in the HF band, you might have heard whistlers in the Earth's ionosphere, magnetosphere. Well, this is sounds the same, but what you're hearing here, each pop that you heard before, those we call them S bursts, short bursts, has this characteristic spectral signature, and that is caused by the electrons actually moving in the magnetosphere of Jupiter. And by the change in frequency there, you can actually determine how the electrons are moving. In this case, they're moving outward along the magnetic field lines. And the cartoon over here on the right shows you the kind of the signals are amplified and sent out in sort of a conical pattern. And when that cone is aimed towards the Earth, we have a higher probability of picking up those Jovian emissions. So that's kind of fun to actually hear the sounds of solar and Jupiter bursts. And so that's part of the motivator. That's part of the education and to try to get people interested in radio astronomy, is that you can give them this hook of hearing the signals coming from these different objects. So as you know, we can do this from the ground because there's a nice big radio window. So we can do radio astronomy fairly inexpensively and fairly simply and fairly easily using ground-based equipment. So there's a very, very large window, and the lower frequency end, they're around 10 megahertz. That is an ionospheric cutoff. So Earth's ionosphere will absorb or reflect radio signals of lower frequencies. So if you want to do radio astronomy at frequencies lower than approximately 10 megahertz, you've got to go into space. But frequencies higher than that, you can do most of your observing from the ground. And of course, you need big wavelengths, you need big telescopes, big dishes. So most of the radio astronomy we know of is done with these big dishes or large arrays of dishes. So the technology, as I mentioned before, is getting much better at taking individual dishes and putting them all together and creating, doing imaging even at low frequencies. And you could even go down to the itty bitty radio telescope and use a satellite TV dish to do some very simple radio astronomy. Radio JOVE, as I said, is at the HF band, so around 20 megahertz. That's 15 meters wavelength. So that's a heck of a large dish. So we use wires, and that's a very simple way of capturing the radio waves. And so we use half-wave dipoles. And so you see it there on the lower right. That's to scale essentially. And a single dipole works pretty well. And we actually pair two antennas, two dipoles together to give us a little more gain to pick up the weaker Jupiter signals. The solar bursts are strong enough you can actually pick those up with just a single dipole. So the last slide on some basics of radio emission is, what are the sources? Well, you've got solar system sources. You've got Jupiter-like planets, of course, the sun. The Milky Way itself is emitting radio waves. You've got other galaxies, quasars that are emitting radio waves, even molecular sources. So the two basic kinds of mechanisms, of course, is the thermal emission, and that's what we typically deal with when we see a hot object that's emitting thermally. Now, that's of course black body radiation, and you can get thermal emission due to interactions of charged particles and free emission, or the transitions and spectral lines. But typically, if you remember what a black body curve looks like, you need an extremely high temperature object to emit a lot of low frequency, long wavelength radio waves. So a star typically does not emit radio waves thermally. Now, they emit non-thermally, and all that means is that that's the plasma. So you've got cyclotron or relativistic electrons in magnetic fields, so you get synchrotron emission. The plasma combined with the magnetic fields gives you the mechanism to emit very strong radio waves via this non-thermal mechanism. So, and some of these mechanisms are maser type. So like a laser, they're amplified, stimulated, amplified, and so you get this coherent emission from these sources that you can detect from a very long way away. And if you have a dish type radio instrument, radio telescope, you essentially are making a radio distribution map. And so we can, at a very simple level, we can do that too with simple equipment. But as I mentioned, you need some bigger dishes to create maps. So the question, I got a question in the chat about where is the itty bitty. Let's see if I can go back to that. I don't know where you talking about. Where is this one specifically, or so you can convert your a direct TV satellite dish with the right detector on there. You can actually pick up a signature from the sun. Now it's a very wide beam, and so you just get a very simple increase of emission. But you can detect, say, a person walking in front of your antenna sometimes, or if you point it at the sky and point it at the sort of the trees, you can detect the difference and the sky versus the tree temperature. You can use essentially a thermal telescope there. But there's plans on the web about how to use one of those and make one of those. So what is Radio JOVE? So Radio JOVE has been around a little over 20 years. So myself and a few other colleagues started this as an education outreach project while I was at NASA Goddard. And it was a simple way to build your own radio receiver and your own radio antenna to have a working radio telescope that you can actually use. You can use it to pick up solar or Jupiter radio bursts, and you pick up the galactic background from the Milky Way. So that involved you actually soldering and building the receiver itself, but we're having really a hard time getting those parts, and so we stopped selling those kits last year, and we've transitioned into using off-the-shelf spectroscopes, the software-defined radios, we call them, SDR radios. And so it's just a nicer tool to be able to, again, build your own radio spectrograph to observe Jupiter, the Sun, Milky Way, and even Earth-based radio signals. And our goal is, of course, to get people interested in science. We hope that we can provide a path. We're attempting to try to provide a pathway to allow someone to become more advanced and to become a citizen scientist and contribute, science quality data to our data archive and use that to, write papers or give professional talks. So, we want to provide a hands-on experience, so you actually can use your own equipment. We have ways. I'll demonstrate a way to kind of get involved in the beginning to even without equipment. You can see some live streaming data, online observatories, and exchange, interact with other amateurs, but also professional radio astronomers. So the hardware and the software is geared really for someone at the high school level or beyond. And so you're a club like yourself, of course, is very well versed in astronomy in general. And so making a switch to, I'm going to try to convert one of you maybe to a radio astronomer. But so any the general public who's interested, radio enthusiasts, and science classes. We've had several universities, get involved, and we're hoping to expand our group to try to do more science, get more of these instruments set up around the country. So here is the instrument. Here is the basic setup, and we're using the commercial receiver from SDRplay. So that's a UK-based company, and we pair it with our dipole or dual dipole radio antenna, and we've chosen the size of the antenna there. You cut the antenna to the range of frequencies that you want to detect, and we've cut the antenna to 20 megahertz because that's and plus or minus 4. So these SDR radios have about 8 megahertz of bandwidth, and so from 16 to 24 megahertz, that's a good band to pick up Jovian radio signals. Above 24, 25 megahertz, Jupiter emits all the way up to about 40 megahertz. That's a magnetic cutoff due to the strength of Jupiter's magnetic field. But the signals get very, very infrequent above 25 megahertz. So we stay on the lower end there. And of course, so Jupiter is a broadband emitter, so and so is the sun, and so is the Milky Way. So in this band, you could easily pick up all three. And it's very simple. I have one connected here, and I'll see if I can switch over here in just a second. But we pair the antenna with the receiver, and then you connect it to your computer via some software, Radio-Sky Spectrograph software. So he's one of our, Jim Sky wrote this software, and he's part of our team. And so it's a display software. So it's what you're seeing there is a frequency time spectrograph. So on the y-axis, you've got 16 to 24 megahertz. On the x-axis, you have universal time. And the third dimension, the color there, shows you sort of the intensity of the signals. And what you're seeing there is some solar bursts there, those vertical stripes there. The horizontal bands typically are interference. And I'll show you some of that here in just a minute. So I want to stop sharing and show you this, my browser real quick. I have to hit play here. And let me share that. If I can find it here. I think that's it. I hope you can see through this. So one of our observers in North Georgia, in Jasper, Georgia, rigged up his radio, and he's got it live streamed on YouTube. So I'm a few minutes off here because I started this at the end of the talk here, so the timing isn't quite right. But the data there are live data from his spectrograph. We've also got a second observer connected, and that's a single frequency, original Radio JOVE 20 megahertz receiver. And so the audio is actually coming from the 20 megahertz signal. Is there another question? Oh, let me pause. Sorry about that. Let me pause my, I'll pause that, and so you can hear me a little better now. Sorry about that. So without any equipment, you can actually look and listen to his live stream data, and listen for solar burst or Jupiter burst, whatever. The map here on the right, I'll mention this here in just a minute, but it's a probability map of when the best time to observe Jupiter is based on the orbital position of Io. So he's got that map up there showing you that. So that's one cool way to get involved with a live stream there. And I want to show you I have a radio connected to this computer, and let's see if I can share that here. And so I'm just in my office here, and I have the radio. I'm going to try to pick this thing up, and it's probably going to give us some weird signals, but that's my radio, and I have it connected to a dipole antenna that's just sitting here in the corner of my office. So I'm not really doing a very good job here. I'm getting a lot of local interference here. So the horizontal bands there is all kinds of local radio frequency interference, RFI, coming from the building, coming from my office. And so not terribly exciting there, but that's real-time data, coming from my office. But what I wanted to show you here, if I can do this, let's see if I can stop this, the software allows you to go to what we call a client mode. And then I know this one was working. It was 20 minutes ago. This guy is the same one in Georgia. He is, the same data is streaming, and the software is free, by the way, so you can download this. And so now there's no sound here, but this is live data using our Radio-Sky Spectrograph software. And so this is the same guy in Georgia that's streaming. So anybody who has an internet connection can, with their computer, can live stream their radio data. And so this is Larry Dodd is his name. And so he's streaming data. And so, you know, you don't even have to set up an antenna at your site. You can actually record using this client mode and record data. And these data would be saved on your computer to go back and look at or for analysis. So some of the horizontal bands that you see here are local stations. So you can actually pick up some of those local stations. You've got intermittent horizontal lines there. Those are RFI, you know, something turns on, turns off. Oh, these slanted lines that you see at the coming up from the bottom there. This is really interesting. This is radar. This is what we call a radar sweep. And we pretty much determined that these are coming from the Gulf Coast. So these are ionospheric sweepers that go right up through a whole series of frequencies, and they're sounding the ionosphere. So you get a signal bouncing back off the ionosphere at different frequencies. And so some of those are sounding the ionosphere to understand the properties of the ionosphere over as it changes diurnally. We think some of these are sounding, these radar sweepers are also looking for, you know, illegal activity out in the Gulf of Mexico. But there's a very, very strong signal, as you can imagine. And so this is actually being picked up in North Georgia very clearly. So it's a sweep right up through our band here, the HF band. So that's a really great way to determine that your antenna is actually working properly. So that's kind of neat. Let me stop sharing that briefly here and go back to chat here. Is there a question? Yeah, good question. Someone asked about is there a way to reduce the RFI? So as an optical astronomer, of course, you're running away from light pollution, right? It's just encroaching everything. Radio astronomers, we have the same problem. The radio interference is encroaching everything. So we have to get more and more and more remote. Depending on your location, you know, rural sites obviously are typically better. Sort of major cities, industrial areas typically aren't very, very good, but anybody's a ham radio operator, right? So we're operating in the ham band. So it's, if you can use a ham radio, you can do some radio astronomy. It's the same basic equipment. Now you've just got your antenna pointed typically upward as opposed to pointed towards the horizon to pick up communications. So with radio astronomy, especially with a large bandwidth, and that's a great thing about these wideband radios, you can get some interference at some channels, but then you can have some channels that are fairly clear. So you can still do some radio astronomy. You can clean the data or remove those channels, but it's a huge problem. Some people, have antennas set up in their backyard, and there's power lines running down their street, and they have no problem. Or their house is, insulated enough, or you can try to rectify things. You can put filters on things and try to reduce the local RFI as best you can. There's a whole, I wouldn't say an industry to try to do that, but there's a lot of talented people out there that know what certain RFI sounds like, and they can tell you, oh, that's probably if you've got some fluorescent lights in your house or in your garage or something. Sometimes the ballasts are very, very noisy. We've had terrible RFI from certain even LED lights if they're not well insulated. Power lines, leaky transformers, arcing transformers are terrible, but some of them are perfectly fine. So some sites work very, very well, and others are very poor. And there's not a real easy way to test it without just simply setting up an antenna there, a test antenna, to see what your local interference is like. So it's a constant problem. We're trying to help people who have antennas set up in different locations, and sometimes people go and turn on and off breaker switches in their house to see whether the air conditioning is causing a problem, or again, certain lighting. These touch on off lamps are terrible. We found that electric blankets are horrible radio emitters. You wouldn't think of that, but they are so bad that you simply unplug it, and your site becomes 100% better. But it's a big problem, and we're doing our best we can to try to mitigate it and help people mitigate it. But as I said, just like optical astronomy, it's becoming worse and worse and worse. I'm going to get back to where I was here. But that's a good question. So I'm glad you brought that up, because it's something I wanted to address anyway. So let me start this here. And so, yeah. So for us, the nuts and bolts of it, if you wanted to get involved here, all the stuff, all the plans for our radio telescope are on our website. So you can buy the receiver commercially if you'd like to. You can build your own dipole. You don't have to buy anything from us, but we offer it as a kit just to make it easy for people to get involved. So if you want to solder your own antenna, you can, the cost for the receiver and the coax, the copper wire, is $215. Now you have to go and purchase your own antenna masts and some rope and tent stakes to put the antenna up, and that could be another $100 or so. But if you don't want to solder and you want to have your antenna built for you, you see the price goes up quite a bit there. Someone asked about VHF or UHF with a smaller antenna. Yes, you can certainly do radio astronomy at those bands, but those you're going to be the ionosphere is going to be a problem to do radio astronomy. That's the issue. Is you're going to see Earth emissions there. You're not going to get a whole lot of extraterrestrial signals at those bands, because the ionosphere is gonna get you. So that's part of the issue. But yes, if you can you can do some solar radio astronomy at at VHF. They have, I'm trying to think, there's a solar SID telescope that you can get. I think it's out of Stanford. And it's at, oh gosh, I forgot what frequencies they monitor, but you can wrap your own wire antenna and pick up some solar ionospheric disturbances is essentially that way. There are all kinds of different antennas. You don't have to use a dipole type antenna. There's people have had some success with a large loop. As I said, you can use a Yagi pointable antenna, but they have to be quite large, you know, at these frequencies, and that's part of the hurdle of overcoming, at least getting involved with Radio JOVE, is some of the antenna have to be quite large. But people have tried different things and had some success with, as I said, some meter size loops. There's it's like a 2-element. You can use a 2-element, like a Moxon antenna, they call them, which is a Yagi type antenna that you can point. So there's a whole art and science to building and designing some antennas to do radio astronomy at these wavelengths. So it's a lot of fun. There's a lot you can do there. So just to talk a little bit about some of the observations that you can make with Radio JOVE equipment. So I've shown you, and you've heard some solar burst. You can, and I've talked about these radar sweepers there in the lower right, and there's some solar bursts sort of in the background there. Some of the Jupiter bursts there in the lower left have some very interesting spectral signatures. That's another way you can detect or tell that it's Jupiter, and for solar emissions too, that there's a certain spectral signature. So these wideband antennas, these radio spectrographs, allow you much better success in identifying an extraterrestrial signal, Jupiter or solar signal, versus a local interference. And a great way to identify something on your telescope is to compare it with someone else's observation, and that really is a great way to eliminate anything local. If solar burst should be detectable by everybody, and a Jupiter burst by everybody. So if you pick up something and someone else doesn't, typically that means you're probably getting something, some local interference. We get these terrestrial propagation. So these triangular shaped structures are really cool. We've actually got a paper written about these things. So these are generated by distant lightning. So lightning, by the way, Radio JOVE at these HF bands, they're a very good lightning detector. You can hear the pops and see the lightning show up very easily on your spectral chart there, and you can pick up distant lightning very easily. But in between, sometimes, unless you have a local thunderstorm or something, you typically want to unplug your antenna from your system. But the lightning is typically short term, an hour or two, and then your signal becomes cleaner. But certain distant lightning actually reflects off the ionosphere, and you get these weird looking triangular structures. And so we're studying these to try to understand what the nature of the so the lightning emits optically. You get sound, but you also get a lot of radio signals generated from lightning bursts. And so this is a distant lightning hundreds of miles away that reflects off the ionosphere and down to and it's a moving thunderstorm. So you get this triangular shape because this thunderstorm is actually moving, and we've never seen these before until we started, using more and more spectral data, and we've seen those at multiple sites. So we're actually I have a student doing last year and now over the summer, looking at some of the data to analyze these terrestrial events. This other image here shows you another solar burst. So that's a 20 megahertz single frequency in the red in the background there, and then sort of overlaid is the spectral data. So you can see some very interesting spectral signatures of some of these solar bursts. Matter of fact, if you know this, type 3s are the most common, typically due to a very brief and intense solar flare, but you've got type 1, 2, 3, 4, and 5 solar radio type bursts. And so each one is caused by a different structure due to the sun and the magnetic field and the plasma around the sun. This signal on the right shows you another interesting feature. So when a solar flare happens, of course, you get the ionosphere becomes very, we call absorptive. So you have ionospheric changes diurnally. So you have a daytime and a nighttime ionosphere. When the solar UV causes the upper layers of the atmosphere to dissociate and become a plasma. So you get a lot more plasma during the daytime. And then that plasma recombines somewhat over at night. But during the day, if you get a solar burst, sometimes that very intense solar UV will cause even more dissociation in the ionosphere, and that makes the ionosphere even more absorptive. So you get what we call radio fade outs. So you get communication losses, right? So your ham radio people know this. You get signals that would normally bounce off the ionosphere, then get absorbed, and you can actually see that absorption here in the spectrum, and even some of the individual radio channels that you see here at the top of the spectrum, you see them kind of get fainter due to this the absorptive nature of the ionosphere. So, and you can trace in some cases, we can trace this back to a particular solar flare, an M type or a C type, or the stronger ones are called X flares, X type flares. So that's an interesting way to analyze the nature of the ionosphere, doing some radio astronomy there. So the very simple equipment that we provide is sort of an entry level system, but we also have some advanced hardware. We have wideband antennas, and then we can actually put these antennas into a square. So instead of two dipoles that are operating together, and by the way, you can take those two dipoles and point the antenna one way or the other using delay lines. So it's in a sense, you can actually steer your antenna, even though it's fixed. You can steer it using delay lines. But you can also take four dipoles, two this way and two this way, and create essentially a square. And that's a very simple dipole array. And with the right combiner, you can actually turn this into a polarized antenna. So you can detect, so the individual dipoles detect linear polarization. Well, in a square array, you can actually detect circularly polarized emission, both right hand and left hand circular. And we do this because Jupiter, by the nature of the emission mechanism, these spiraling electrons in the magnetic field of Jupiter, it's a cyclotron process. Those emissions are almost 100% right hand or left hand circular. So you have a better way, a better opportunity to pick up Jovian signals with a polarized antenna. And so you can actually create your own polarized antenna, polarized square array there. We have a way to calibrate the signals. So the system that we have now is an uncalibrated system. So it's essentially a relative intensity scale there. But the problem here is, as you know, doing optical astronomy, you can buy some entry-level telescopes at a few $100s to get a reasonable telescope for a beginner. But anytime you want to do a more advanced system or do some imaging or whatever, it quickly gets into the thousands of dollars, as you well know, and that's no different here. So you get a wideband antenna and a calibrator, you're up to a few $1,000s very quickly. And we're trying to improve our data. Our advanced observers have some of this equipment with better timing systems, and so we're trying to ultimately do a little more science to better understand the solar emissions or the ionosphere and that nature. But so that's an opportunity for someone to advance and get more involved in radio astronomy. And so we do have a data archive at our website, and we allow beginners to upload their data to our data archive. We want people to become involved, and we want to have an archive to allow people to put their data there, and also allow other people to compare data with someone else's data. And even our more advanced data are being archived at professional archives. So we're hoping that the more sites that we have, advanced sites, we can, as I said, do some more science with them. So we have professional archiving done. Some of the citizen science that I've already mentioned here is looking at Jupiter and solar emissions, even the galactic emissions, and making calibrated science quality observations of those sources. And we have observing campaigns to try to allow people to be a little more successful observing. So especially for Jupiter, we can actually predict when Jupiter will be more likely to emit radio waves, again, depending on the location of Io in its orbit. So we have these probability maps. So we actually build over many years a probability map. And so one of our citizen scientists is doing that and making some very subtle, some discoveries, polarization, observations that haven't been seen before. So that's kind of exciting. We want to have people at their site make what we call a quiet day curve. So essentially, what's the galactic background level at your site? And we know that there is a latitudinal distribution of the ionosphere, the equator up to the pole. So what we want to do is to get enough data points to try to characterize what the galaxy, the galactic background, the Milky Way galactic background would look like at a different latitudinal distribution of that. Studying how the radio waves propagate through the ionosphere. So one of our NASA collaborators is an ionospheric physicist. So we're and he's the one that wrote the paper on the terrestrial propagation and trying to understand how the ionosphere behaves through as the radio waves propagate. This graph at the bottom was something I started back in 2005 just as sort of fun to count the number of solar radio bursts with the old Radio JOVE equipment, just looking at those type 3 solar burst events and plotting them on a long-term basis. And so you can see how the sunspot number there, that's this is monthly averaged sunspot numbers, monthly averaged 10.7 centimeter radio data, and then the Radio JOVE solar radio burst counts, how they compare over the long term. So we've stopped there in about 2018, but I'm hoping to have someone go backwards and fill in this plot now that we're building back up towards solar maximum. So in 2025 or thereabouts, we'll have our next solar max, and we get a lot more solar radio burst, as you can imagine, during solar max than we do during solar minimum. So that's, and I'm hoping that we might learn something new using the solar radio burst counts. It might lead us to something new about how the sun behaves magnetically over solar cycle timescales. So I've mentioned a couple of these. So some of our highlights here is that a recent paper on these terrestrial propagation events, the lightning events. We've had some of our citizen scientists actually give papers at professional conferences now, and I've had a couple of students use Radio JOVE data at conferences, and we've got about 12 active citizen scientists, and we're hoping to add more people as our capabilities get better, and now the equipment is getting better, and if you are interested, this guy Tom Ashcraft, he's an artist actually at heart, and he's a great photographer. He has been involved with Radio JOVE for a long time. He's an auroral. He studies. Sorry, yeah, I guess he's made photographs of some aurora, but he's in New Mexico, so he doesn't get too many aurora down there. But he has made some of the best photographs of sprites, which are ionospheric lightning, essentially going upward into the ionosphere. If you've ever seen some of those photographs, he's made some of those. So look him up on the solarsystem.nasa.gov. They did sort of a profile of Tom here in the last year, and it's really it's a pretty short read, but it's very fascinating. And he's been part of Radio JOVE for a long time, and he's a great observer for us, one of our best observers. So that's just a few highlights here recently, and I'll end it here, kind of summarize that we've made a significant change here in March. Essentially, we transitioned from the old Radio JOVE equipment, which, matter of fact, let me just go forward here. I'll just show you this. I have some extra slides. That's the old receiver. So that one operated at a very, very narrow band at 20 megahertz or 20.1. And that's the receiver you actually built yourself. And that was a lot of fun, and people had a great time building and operating those receivers, but we just kind of ran out of gas finding parts for those things. And so these commercial digital receivers are so easy to use and so much better. We've made this shift, and so we hope that excites people, gets some more people involved in radio astronomy this way. And we're in the midst of trying to develop sort of training tools to train people to go from zero, to beginners, to more advanced levels of doing some radio astronomy. And so we have an active listserv now, and our website's been sort of revamped here recently, and our data archive has been upgraded. So, we're looking for people to get involved with radio astronomy. So if you have an inclination to do that, please reach out to me. If you, I think certainly Ed and Linda have my contact information, so you can contact me directly, and I'm happy to, answer questions about the equipment or help you get involved if you're inclined to do so. So I'll stop here and have some time to answer questions. I really appreciate your attention, and again, I appreciate the invitation to speak to you. So thank you very much. Great question. So meteor. So yes, you could observe meteor reflections. So radio reflections off of meteor trails. So it's a very tricky observation, as you can imagine. So you have to have a known radio emitter, a known station, terrestrial station, and of course, if a meteor comes through the ionosphere, it sort of ionizes, you have the ionized tail. And so the idea here is that the radio transmitter that would not be heard due to the orientation and the ionosphere, whatever, then becomes heard for 30 seconds. 45 seconds, or however long that meteor trail provides the ionization to allow the reflection off of from a known transmitter. So people have done it, yes, at these low frequencies, but it's very, very tricky because you have to have the right orientation and you have to know where that signal is coming from, and sometimes if you've got interference, you don't know, was that just random interference, or was that a signal coming from a meteor? And of course, if you can observe the meteor optically, all the better. That's a true test that you've actually made that observation. But yes, it's possible, but very, very tricky. Good question.
Thank you so much, Chuck. I'm Jim, and I must say that my first two loves in early teenage was astronomy and ham radio. And after 50 years, I've taken up again both. So this is a wonderful introduction. I'm not sure I understood. I posed that question about VHF and UHF because the antennas would be smaller. I live in an apartment. It's fairly crowded around here. So I'd like to be able to take something portable, and obviously those dipoles are not going to do it. So I thought higher frequency, smaller antenna.
That is true. Again, the problem is, what are you trying to observe?
Right. And that's what I'm asking too.
Yeah. So you can pick up a solar burst with a higher frequency. And therefore smaller antenna. I'm trying to think. I guess the other thing about the beauty of these SDR radios is they have extremely broad band. You go up to a couple of gigahertz even with some of these. So that might be possible with a smaller antenna. I have to think about what type of antenna, or what your best
right.
method would be there. But
I saw it was on a ham radio presentation, but like an umbrella, that you can unfold and make a parabolic, and the thing was a good 6 or 8 feet in diameter when it was unfolded. And
well, sure, yeah.
But
so if you're going to a dish, yeah, that provides its own kind of complications. Again, how big, but sure, if you can have something unfold, then you might be able to easily carry that around.
But the synchrotron radiation from Jupiter tends to be lower frequency than the 15-meter area.
The synchrotron is going to be higher frequency.
Right.
Yeah, but then you're going to need a dish to get enough gain to actually pick up those signals. Typically, to detect the synchrotron, you're going to need a fairly large antenna because it's just not strong enough.
And what is the interaction between Io and Jupiter? What kind of radiation is that?
Yeah, so that's the cyclotron. So it's basically non-relativistic electrons. But the beauty of this sort of situation is that what happens is that you get the signals are getting amplified. So it's a very narrow kind of beam of radiation, and so it's not broad. And so because it's sort of narrowly focused by this maser type mechanism, so it's coherent radio signals pointed at Earth or wherever, you can actually pick those up with a very, very simple antenna. And the synchrotron stuff is not, that doesn't happen. And so you need a bigger dish or a bigger antenna to actually pick up the a little bit weaker signals in that sense.
So the maser is a lower frequency, like you're saying.
Yeah, that mechanism by which that emission is emitted is sort of fortuitously sort of focused and therefore stronger, and we can pick it up easier with a ground-based, a simple ground-based radio antenna. So a single dipole could do it, but we use two to give you a better chance to pick up some of that weaker Jupiter. But with a small radio dish, I don't think you'll pick up the Jovian synchrotron. I think it's just not strong enough. You'll need a bigger dish.
I'll reach out. Thank you so much.
Oh, you're welcome. Any other questions? Well, thank you very much again. Enjoy your Saturday evening.